Hello everyone, today we are diving into the fascinating world of inorganic chemistry, and for our CHM361 course, we will be exploring why transition metals are such powerhouse players in the world of chemistry, specifically their role as catalysts. Before we start, I would like to introduce my group members. I am Khadija and my friends are Alia Nasuha, Nur Akila and Najwa. For our presentation on transition method as catalyst, I will be covering our core objective and the scientific reason why these specific methods are so vital to the chemical industry. Our main goal is to define transition method and identify their unique electronic configuration, to examine the catalytic properties of transition metals to evaluate their roles, to explain why transition metals are effective catalysts, and lastly to describe real-world examples of transition metal used in catalysts, including their roles.
So, what is transition element? Transition elements are elements located in the D block, which is groups 3 to 12 of the periodic table that contain partially filled d orbitals. So they have some general properties for this topic. First, we have high melting and boiling point. They are usually require very high temperature to melt or boil. Second, hard and strong. Most transition metals are physically tough and resistant to deformation. And the third one is good electrical conductivity. They are efficient conductors of electricity. Next, we have magnetic properties. Some transition metals can be magnetized. And the last one is form-colored compounds. Their compounds often display bright and distinctive colors. Also, it acts as catalysts, which is they can speed up chemical reactions without being concealed.
Okay, so without further ado, we are looking at transition metals are effective catalysts primarily due to two factors, which is their variable oxidation states and their ability to absorb molecules. This allows them to form unstable intermediate compounds with reactants. By doing this, they provide alternative reaction pathway that has a significantly lower activation of energy. For example, take the reaction between iodide and peroxide disulfide ions. This reaction is normally slow because both reactants are negatively charged and repel each other. However, Fe2 plus and Fe3 plus ion can help step in acting as an electron bridge to facilitate the reaction smoothly. The second factor is the ability to absorb molecules. This is the common in heterogeneous catalysts, where the metal is a solid and reactants are gases and liquids. The metal surface provides active sites, which is think of this as parking spot for molecules. The process happens in two steps, which is first adsorption. Reactant molecules land on the surface and form weak bonds with the metal. This stretches and weakness in the internal bonds of the reactant, making them much more active. And the second one is desorption. Once the reaction takes place and the new product is formed, it breaks away the surface. This leaves the active site empty and ready to help the next of the reactants.
Now I represent about mechanism of transition metal as catalyst. One of the mechanism is change in oxidation states. In this mechanism, transition metals can easily change oxidation states, allowing them to accept and donate electrons during reactions because 4s and 3d electrons can be lost or gained easily. The metal reacts with one reactant and changes its oxidation states. It then reacts with another reactant and returns to its original oxidation states. This provides an alternative reaction pathway with lower activation energy. Lastly, the ability of transition metals to exist in several oxidation states makes them effective catalysts in redox reaction. Next, surface adsorption mechanism is one of the mechanisms of transition metals as catalysts. In this mechanism, the reactant molecules attach onto the surface of the metal catalyst. The metal's catalyst partially filled d orbitals interact with the electrons of the reactant when the molecules are adsorbed, and it will form temporary bonds. Adsorption will weaken existing bonds in the reactant molecules. When the bonds are weakened, the activation energy is lowered because less energy is required for the reaction to occur. After that, new bonds are formed between the metal surface and it will produce the reaction products. Lastly, the metal catalyst remains unchanged and can be reused for many reaction cycles. One of the examples for surface adsorption mechanism is Haber process that use iron as catalyst. In Haber process, iron acts as catalyst by providing a surface on which nitrogen and hydrogen can react to form ammonia. The iron surface lowers the activation energy of the reaction. So, this allows the reaction to proceed at a faster rate and the process will become more efficient. This will improve the efficiency and makes the larger scale production of ammonia.
Next, I will explain about the application of transition metals, especially in their role as catalysts in industry and daily life. First is the Haber process. This process is used to produce ammonia, which is very important as a raw material in the fertilizer industry. In this process, iron, which is transition metals, act as catalysts. Iron provides an active surface that allows nitrogen and hydrogen gases to adsorb and react more efficiently, increasing the rate of ammonia production. For the second one, we have catalytic converter, which are used in vehicles. Transition metals such as platinum and palladium are used as catalysts. They help to reduce harmful exhaust gases like carbon monoxide and nitrogen oxide. As a result, this process helps to reduce air pollution and meet emission standards. Lastly, we have hydrogenation of vegetables oil. In this process, nickel is used as the hydrogenous catalyst. Hydrogen is added to unsaturated vegetable oils, converting them into saturated fats. This changes liquid vegetable oil into solid or semi-solid products such as margarine.
So, for the last part is conclusion. Transition metals are distinguished by their partially filled d orbitals and ability to exist in multiple oxidation states, which make them highly versatile catalysts. They provide an active surface that allows reactant molecules to attach and form temporary bonds. This interaction weakens existing molecule bonds and helps position reactants in a way that increases the effectiveness of collisions. As a result, the activation energy required for a reaction is reduced. These catalyst properties are essential in many important applications, including the industrial production of ammonia and fuels, the reduction of harmful vehicle emissions, and the production of clean hydrogen energy. That's all from us. Thank you.